The topic is complex numbers. Now we're going to talk about this, I. We know that with the real numbers, we cannot take the square root of a negative number, which means up until now, we couldn't take the square root of negative 25. It wasn't negative 5 because negative 5 times itself is positive 25. So negative 5 is one of the square roots of positive 25, but it's not the square root of negative 25. There is no number times itself that gives us a negative number. And for various reasons that we're not going to get into, mathematicians found it very useful and made math work more. I'll just put it that way. If they said, hey, we're going to create a number. The number we're creating is the square root of negative 1, and we're calling it I. I is the square root of negative 1. And from this rule, I equals the square root of negative 1, comes this masterpiece here. I squared is negative 1. And this rule is just as important as I equals the square root of 1, if not more so. Because as we're going to be doing our math with I's, are you excited yet? Whenever we see an I squared, we're going to replace it with a negative 1. How does this work? Okay, I said the square root of negative 25. Well, we have a rule that says underneath the radical, we can break it up. And I'm going to break it up so that my negative is a negative 1 times the other thing. And then I have the square root of negative 1 times the square root of 25, which is I times 5. Or 5I. So the square root of 25 is 5I. Why? Because I is the square root of negative 1. Who said? They said. Who's they? Doesn't matter, not important. But we know that the square root of negative 25 would be 5I. Let's take a look at the square root of negative 12. Well, a lot of this is going to be a review. We have one new step. That one new step is that negative 12 is negative 1 times 12. So this is the square root of negative 1 times the square root of 12. In other words, I times whatever the square root of 12 is. We can't leave it that way. 12 is 4 times 3. Square root of 4 times the square root of 3. I times 2 radical 3, or how we're going to write it, 2I radical 3. So either 2I radical 3, or we can put the I at the end and we can write 2 radical 3I. But again, if you write it this way, you need to be very careful that you're not in any way writing that square root sign over the I. There would need to be a very clear ending above the 3. So that's why I make it 2I radical 3. I don't want there to be any confusion when I write this. But either of these is correct. Okay, what about something we wouldn't be able to simplify further if it was a positive? What about the square root of negative 13? By now, you should be realizing that a negative underneath is just an I outside. We can't simplify the square root of 13 anymore. So the square root of negative 13 would be a very quick I radical 13, or again, radical 13. I being very careful, and this is already questionable, being very careful to have a clear separation. That square root is not over the I. Okay, let's have some fun with this. The square root of negative 9 times the square root of negative 25. So we're going to have a rule for these problems. The negative on the inside becomes an I on the outside first, every time, without question. That is the first step. Why? Well, then this one becomes 3i, and this one becomes 5i. 3i times 5i is 15i squared. And what was so special about I squared? Well, I squared is always negative 1. So our answer is negative 15. Let's do another. Square root of negative 15 times the square root of negative 3. This would be I radical 15 times I radical 3. I times I is I squared. Radical 15 times radical 3 would be radical 45. I squared is always negative 1. Radical 45 can be 9 times 5. Negative 1 times radical 9 times radical 5 would be negative 1 times 3 times radical 5, which would be negative 3 radical 5. Why did I say it is? I'm going to put it a different way. It's super de-duper important, okay? It's that important that I just said super de-duper. It is super de-duper important that the I's come first. Because if not, if you do it wrong, something horrible is liable to happen. This is wrong. Do not continue this part of the problem thinking that it is right in any way. This is wrong. Negative 15 times negative 3, that would be positive 45. And then the square root of positive 45 would be 3 radical 5. But is 3 radical 5 the answer? No. Negative 3 radical 5 is the answer. If you get positive 3 radical 5, that means you multiplied negative 15 times negative 3 first, which is wrong, because what has to be the first step? What is super de-duper important? I radical 15 times I radical 3. Then go on and do your stuff. But that I times I is I squared, which is negative 1. which is where that -3 comes from. Super duper important. It's not so much an issue. Oops. It's not so much an issue with division, though. You'll still accidentally get the correct answer. Let's say we had the square root of -50 over the square root of -2. Well, we don't have to worry about rationalizing or anything like that yet. But what we can do is make this I radical 50 over I radical 2, and then those i's cancel. Radical 50 over radical 2. And square root over square root can also be written as the square root of the fraction. Why did I do that? Well, because 50 divided by 2 is 25, and the positive square root of 25 is 5. The answer here is 5. I said don't worry about rationalizing or anything, but from this step, from 50 over radical 2, what if you did rationalize? Multiply by the square root of 2 over itself. That would be the square root of 100 over 2, which would be 10 over 2, which is also 5. Rationalizing gets us there as well. Either way, we want to get the most simplified answer possible without factors of a square root, without perfect square factors under a square root, and without square roots in the denominator. Square root of -48 over the square root of -3. I radical 48 over I radical 3, which is radical 48 over radical 3. And I would make this radical 48 over 3, which is radical 16, which is 4. That's one way to do this. But by now, hopefully you're realizing do correct things and get correct answers. Maybe you simplify the top. 48 is 16 times 3. So this is radical 16, radical 3 over radical 3. Radicals 3's cancel. Square root of 16 is 4. Or maybe you just rationalize. This one might be a little bit more difficult, but times radical 3 over radical 3 gives you the 3 on the bottom. 48 times 3 is 144. Square root of 144 is 12. 12 over 3 is 4. Lots of different ways to get to 4. Now, when we have something that involves the square root of a negative or an imaginary number in any way, we want to make sure our answer is written in the form a plus bi. That means two distinct parts. One part one term does not have any I in it. The other is the part that does have the I. So I'm going to go ahead and just write A plus BI up here. Wow, that was too high. A plus BI, still a little bit too high. A plus BI, there we go. Up here, so we remember to put our final answer in that form for these. Is there anything we can do to simplify 3 minus radical negative 100? We can make this I radical 100. And what is the square root of 100? 10. 3 minus I times 10, and I times 10 is just going to be written as 10I. Just like x times 10 would be 10x. We work with i's the exact same way that we work with x's. It's just that if we had an x squared, we don't do anything special. We can't do more with it. But when we have an I squared, the I squared becomes -1, and we keep going. This would be our final answer form because we have two distinct sections. The first term does not have any i's. The second term is where our i's are. So the reason that this is in A plus BI form, we could even see it as this, 3 plus -10I. A plus BI. A would be 3, B would be -10 when we have this. And since we can easily identify A and B, it's in A plus BI form. When we have a big fraction looking thing like this, 2 plus 7I over 5, this is not A plus BI form. The top is in A plus BI form. That's the standard form of what we call a complex number. A complex number is any sort of number that involves I. And if you really want to get technical, even 5 is a complex number, because complex number is going to be all of our real numbers plus all of our imaginary numbers. Yes, the I does stand for imaginary. If we take all the real numbers that we've learned so far and combine it with all of the imaginary numbers, we get the complex numbers. And the complex numbers work just like the real numbers, except for that I being the square root of -1. This is not in the final form of a complex number, but if we split it like we did earlier with the radicals into two terms, we're on our way. And then the I can't be in the top. This would be 2/5 plus 7/5 I. Now, my logic here is 7I over 5 would be 7/5 times I over 1. That's multiplication of fractions. And then anything over 1 is itself. So I over 1 is an I on its own. So something like this, since it involves an I, it has to be split into two distinct sections. A plus B times I. A would be 2/5, B would be 7/5 times I. negative 6 plus radical negative 18 all over 9. Let's split. Negative 6 over 9 plus radical negative 18 over 9. Negative 6/9. That's going to be negative 2/3 plus I radical 18 over 9. So I've reduced this fraction to negative 2/3. Negative divided by positive is negative. 6 over 9 is 2 over 3. And now I've done the first step of simplification, which is a negative underneath is an I outside. We can simplify radical 18. That's radical 9 times radical 2 over 9. So we have negative 2/3 plus 3 radical 2 over 9. And I'm going to move the I to the outside. And then there's just one last thing. 3/9 reduces to 1/3. So negative 2/3, sorry for the angle, negative 2/3 plus radical 2 over regular not radical 3 I. And if you need me to put in an extra step here, if the step-to-step isn't making sense, radical 9 is 3, so this is 3I over 9 radical 2. And I moved the I to be floating on the outside because that's what happens to an I on top. Floats on the outside. If you were an I, you'd float too. That's the whole point of it. That was an it pun. Now remember, I did still say we would learn a new way to solve a quadratic equation today. We are almost there, believe it or not. It's actually going to be a real quick thing once we get to it. But I want to do a little bit more with complex numbers first. If we had negative 2 minus 4x plus 5 plus 2x, what would we do? We would drop the parentheses and add, because when we're adding, we don't need to worry about the parentheses. And then we'd add like terms. Negative 2 plus 5 would be positive 3. Negative 4 plus 2x would be negative 2x, and that would be our answer. Would you believe that if I replaced x's with i's, I'd get the same answer? Because that would be true. Here I'm adding two complex numbers. Negative 2 minus 4i is the first complex number, plus 5 plus 2i is the second. Combine like terms. Negative 2 plus 5 is 3. Negative 4i plus 2i is negative 2i. Our answer is in a plus bi form. So we just treat the i's like x's. If we had 3 minus I minus 7 minus 9i, just like we would distribute the negative if we had x's, that's what we do here. So 3 minus I minus 7 minus a negative plus 9i. 3 minus 7 is negative 4. Negative I plus 9I would be plus 8I. No different than if we had x's. Would this be positive 4I, negative 4 plus 8I? No. These aren't like terms. They're two pieces of a complex number. But even if this was an x here, we couldn't combine because it's not negative 4x plus 8x. This isn't negative 4I plus 8I. It's negative 4 plus 8I. Order of operations says multiply before add. So these are joined. You can't take the I off of the 8 to add the negative 4 to the 8. Just doesn't work that way. Continuing to treat our i's like x's. Negative 2 plus 6i times 4 minus 3i. Well, let's FOIL. Negative 2 times 4 is negative 8. Negative 2 times negative 3i is positive 6i. Positive 6i times positive 4 is positive 24i. Positive 6i times negative 3i is negative 18i squared. Combine like terms in the center. 6i plus 24i is positive 30i. And then negative 18 times I squared is negative 18 times negative 1. That's the only new step here. I squared is negative 1. And now keep going. Negative 8 plus 30i, negative times negative, that's positive 18. And then negative 8 plus 18 is positive 10. Positive 10 plus 30i. So when we multiply, it's just like if we had x's. But at any point, if we get I squared, then times I squared becomes times negative 1. Remember, we did those special products. We did rationalization. Adding, subtracting, multiplying, those all work just as if the i's were x's. Dividing is much easier than if the i's were x's. We're just going to combine two of the things we learned how to do today: rationalization and then splitting our answer to make sure it's an a plus bi form. And you might say rationalization, but we did that for radicals. What's I? I is the square root of negative 1. All i's are hidden radicals. So we can't have the I on the bottom. So we have to rationalize. And how do we rationalize? We multiply by conjugates. And might as well put that in parentheses because we have to FOIL up there. On the bottom, we have a difference of squares. First thing squared, 3 squared, minus second thing squared, 5i squared. That will be 9 minus 5i squared would be 25i squared. And remember, multiplying by I squared is multiplying by -1. 25 times -1 or minus 25 times -1, that's going to turn this into 9 plus 25. And 9 plus 25 is 34. So far the bottom is 34. The top is foiling. First, 8 times 3 is 24. Outer, 8 times positive 5i is positive 40i. Inner, 2i times 3, that's plus 6i. And last, plus 2i times plus 5i, that's plus 10i squared. 24 plus 46i, and then plus 10i squared would be minus 10. (24 minus 10 would be 14 plus 46i. So 14 plus 46i over 34. That's how far we've got the answer. But we have to split it up now. 14 over 34 plus 46 over 34. I reduce the fractions. 7 over 17 plus 23 over 17 I. And that is division. 8 plus 2i divided by 3 minus 5i is this. Make sure you can follow every step I did and that you know why we did what we did. Before this point, we could add, we could subtract, we could multiply. Dividing happened, but it was really just rationalization. We never talked about raising I to powers. So an I by itself, that would be I to the first, just I. We know by definition, I squared is -1. And we could use just these two pieces of information to figure out all the rest of the powers of I. For instance, I cubed, we can write as I squared times I. So that's I squared times I to the first. Add the exponents, we get 3. I squared times I. Well, I squared is -1, and I is just I. -1 times I is -I. And then I to the fourth, well, that could be I cubed times I. And we just found I cubed is -I. Times I would be -I squared. I squared is -1. The opposite of -1 is +1. So I to the fourth would be 1. Or you could go I to the fourth is I squared times I squared, which is -1 times -1. -1 times -1 would be +1. Sorry about that. Let me rewrite this last one. So I had said I to the fourth can also be I squared times I squared, which would be -1 times -1, which would also be +1. So what have we found here? Well, I to the first is I squared is -1, I cubed is -I to the fourth is +1. I to the fifth would be I to the fourth times I to the first. 1 times I is just I. Hey, it's cycling. Which means I to the sixth is -1, and I to the seventh is -I, and I to the eighth, that's +1. I to the ninth is I to the 10th is -1, I to the 11th is -I to the 12th is 1. In fact, every multiple of 4 power, so I to the 4n, where n is any number, any integer, positive or negative, but the whole number part. So 2, 3, 4. I to the 8th, I to the 12th, I to the 16th, I to the 20th, I to the 24th, I to the 28th. I to any multiple of 4 power is equal to +1. And we're going to use that as a shortcut to find I to any positive power, I to any negative power, without having to count out the cycle forwards or backwards. Because if I asked you to find I to the 203rd, you're not going to want to sit there and cycle this out. We're going to use a shortcut. Use multiple of 4 powers. So if we had I to the 48th, since that is 4 times 12, that's a multiple of 4 power, that's +1. I to the 13th. What's the highest multiple of 4 power we can fit into 13? 12. I to the 12th times I would be I to the 13th. And as a multiple of 4 power, I to the 12th is equal to 1. And 1 times I is just I. I to the 23rd. What's the highest multiple of 4 power we can fit into 23? That would be 20. So I to the 20th times I to the 3rd. Look at us breaking up these multiple of 4 powers like we do when we're simplifying radicals. It's so funny that simplifying powers of I works like simplifying radicals, huh? Almost like I is a radical or something. As a multiple of 4 power, I to the 20th is 1. 1 times I to the 3rd is I to the 3rd, and then you figure that out any way you have. You can either have it memorized that I to the 3rd is -I, or you can go I squared times I is -1 times I is -I. So you don't even have to have anything memorized except I squared is -1 and I to the 4th is 1. You can figure out everything else as you go. Because this method is going to get us down to either I to the 1st, 2nd, 3rd, or 4th every time. Let's do a few more. I mentioned I to the 203rd earlier. How about I to the 103rd? Highest multiple of 4 is going to be 100. This is I to the 100 times I to the 3rd, which is 1 times I to the 3rd, which is I to the 3rd, which is I squared times I, which is -1 times I, which is -I. These are kind of fun. Anything is fun once you figure out You can do it. I to the 50th, highest multiple of 4 we can fit into 50 is 48. So this is I to the 48th times I squared, which is 1 times I squared, which is I squared, which is -1 by definition. One more. And then we'll move to negative powers of I. I to the 64th. Well, that is a multiple of 4 power. So it's 1, because 64 is 4 times 16. Now, with negative powers, you could still figure out that this is some negative multiple of 4 times something and get your answer that way. I love this trick. When it's negative, we want to push it over 0. So what's the first multiple of 4 we can add to this that's going to push it over 0? And why multiple of 4? Because we can multiply anything by 1, which means we can multiply by any multiple of 4 power, and 20 will be a multiple of 4 that gets us over 19. Negative 19 plus 20 is I to the 1st. So this one's I. Yeah, the pattern will continue backwards. I to the 0 is 1 because anything to the 0 power is 1. So the pattern does continue backwards through the negatives. This also means if you do a calculator or something and you get an answer of 1 over I at any point, this is wrong. This is absolutely wrong. Why is 1 over I incorrect? Because you got to rationalize. This is a radical in the bottom. 1 over I, you'd multiply by I on top and bottom. You'd get I over I squared, which is I over -1, which would be -I. So 1 over I would never be an acceptable answer. It would have to be -I. That tells me when I see 1 over I, that tells me you're using a calculator, because a calculator or a solver will give you 1 over I as an answer. I haven't taught you any way to get 1 over I as an answer. And I won't teach you any way to get 1 over I as an answer because it's an incorrect answer. This gets you the correct form of the final answer every time. One more. Let's do I to the -30th. Highest or first multiple of 4 that pushes us over 30 is 32. -30 plus 32 is I squared. I squared is -1. Next up, we want to simplify I to the 39th. Keep in mind that I to the 4th is 1, and any multiple of 4, I to the 8th, I to the 12th, they're all 1. So the highest multiple of 4 we can fit in is I to the 36. That would be 36 plus 3, that gives us 39. So that's I to the 36 times I cubed, which is 1 times I cubed. We have this down to I cubed now. Let's keep going. I cubed is I squared. Well, let's do this. 2 plus 1. So that's I squared times I to the 1st. I squared, by definition, is -1. So this is -1 times I, which is just -I. The topic is solving quadratic equations by completing the square. 4p squared equals 9. Before today, we would have had to get everything on one side, 0 on the other, factor, and solve. We would get p equals -3/2 or p equals +3/2. Now I present to you the square root property. We are allowed to take the square root of both sides, being careful that when we take the square root of a number while we're solving, we do both plus or minus as answers, because 3 times 3 is 9, -3 times -3 is 9. This would be 2p equals plus or minus 3. 2p equals plus 3. 2p equals minus 3. P equals +3/2. P equals -3/2. Let's see another one. And this is where we're going to bring it all together. (3x² plus 75 equals 0. Instead of doing factoring, we can get the square on one side, the x² on one side, everything else on the other. So let's get the x² on one side. 3x² would equal -75. Divide both sides by 3, x² equals -25. Take the square root of both sides, x equals plus or minus the square root of -25. We couldn't do this before today, but now we know that plus or minus, what's the square root of -25? Plus or minus 5i would be the answer. And let's expand its use to something like this. W plus 3 squared equals 20. Well, to use the square root property, we want to get a square on one side, everything else on the other, and then get rid of the square by taking square roots. Being careful that whenever we take the square root of something, so here the square and the square root are just canceling each other out, but here we're taking the square root of 20. We want to make sure we have that plus or minus sign. Why? Because it's two answers, positive square root of 20 or negative square root of 20, plus or minus, positive or negative. Now, how can we get the W by itself? We could subtract 3 from both sides. Is it going to have anything to do with 23 or 17 on the other side? No, no. No, no. Because the square root of 20 minus 3 can't be done. Square roots of 20 can only be added or subtracted to other square roots of 20. If we had a square root of 20 minus 3 square root of 20, we can do 1 minus 3 is -2 square root of 20. So we would only be able to say the square root of 20 minus 3. And we actually have a shorthand way of writing this. Let's put the minus 3, the subtraction first, and then our radical, plus or minus 20. So actually here, if it was anything but 20, we would be done. Can we simplify the square root of 20? Well, no, square root of 16 is 4, square root of 25 is 5. It's not 16 or 25, but that's not what I'm talking about, is it? We got to look for square root factors of 20, and we got one. 20 is 4 times 5. A 4 on the inside would be a 2 on the outside. So 20 is 4 times 5. Radical 20 would be radical 4 times radical 5, and radical 4 is 2. So I'm going to start doing simplifications like this without showing every step. We got to start doing more things in the problem so we can show less steps, because we got a lot of steps to do. And then we have the minus 3 in front. So W equals negative 3 plus or minus 2 radical 5. That's the answer. And if we had to list them individually, them, what do I mean them? Yeah, them. Plus or minus means this is 2 answers. This is negative 3 plus 2 radical 5, or negative 3 minus 2 radical 5. 2 answers. And again, or doesn't mean you can put one or the other. Or is just how we combine multiple answers. Let's say we had t minus 5 squared. Equals 18. Square root of both sides leaves us with t minus 5 on the left. Square and square root cancel each other out. On the right, we have plus or minus the square root of 18. Let's go ahead and simplify that now. 18 is 9 times 2. A 9 underneath would be a 3 on the outside. This would be radical 9 times radical 2. Radical 9 times radical 2. Radical 9 is 3. T minus 5. To get the t by itself, we would add 5 to both sides. So that's going to be a positive 5 in front of the plus or minus. 5 plus or minus 3 radical 2. Because this means the same thing as plus or minus 3 radical 2 plus 5. We like our radicals to be at the end. We don't like plus or minus in front if there's something we can have first. So positive 5 plus or minus 3 radical 2. As 2 separate answers, that would be 5 plus 3 radical 2, 5 minus 3 radical 2. So it becomes useful to have quantities squared, because then we could apply this square root property. So we would like seeing things like x squared plus 10x plus 25 in a problem, because this is a perfect square trinomial. It factors to x plus 5 squared. We can manipulate the situation so that we are creating squares where squares do not exist. This process is called completing the square. And I'm just going to jump right in. It's a very repetitive process. What would we have to have here to complete the square? In other words, to turn this into a thing squared, what would we have to have here? Well, since it's an x squared, we know that's going to be an x. And since this is a plus, we know this is going to be a plus. The number that's going to go here is going to be whatever half of this is. Half of positive 12 is positive 6. This tells us how to complete the square. What's positive 6 squared? Positive 36. So if we had x squared plus 12x, the number that completes the square is 36. And the square that it completes is x plus 6 squared. This is very similar to a type of problem we would be able to answer in a previous unit. There, maybe it was, what does the middle term have to be for this to be a perfect square trinomial? And how did we find the middle term? This was x squared. This was 6 squared. And in the middle, we did whatever this was plus, and then 2 times the first times the second. 2 times x times 6. And we were able to get that a plus 12x would make this a perfect square trinomial. Completing the square is just doing the same thing, except instead of finding the middle term, we have the middle term, and we want to find the last term. How do we do that? Well, it's always plus. We can make the square at the same time, and it's whatever half is. Half of 12 is 6. 6 squared gives us the 36. So first we take half to figure out what the square we want to complete is, and then we square that number to actually complete this square. So let me line up a few of these. Or I'll just do a couple times. So here, x squared minus 26x, what completes the square? Well, it'll be plus whatever it is. The square we want to complete is x minus, because of the minus here. Half of 26 is 13. 13 squared, and see, this is why it's always plus. Negative 13 times negative 13 is positive 169. What about here? Well, when it's an even number, taking half is easy. When it's an odd number, taking half is not as straightforward, but it's still just dividing by 2. 11 over 2. Yes, really, that's all you have to do to figure out what the square is. Half of 11 is 11 halves. Half means divided by 2. When all else fails, divided by 2. And then square. Squaring 11 halves is going to be a fraction. 11 squared on top, 121. 2 squared on the bottom, 4. So 121 fourths completes that square. Let me line up a couple more. Or maybe 2 more, one at a time. X squared minus 4/7 x plus what completes the square? Let's look at what half of 4/7 is. Divided by 2, we're taking half is the same as multiplying by 1/2. It effectively multiplies 2 in the bottom, 4/14. And then that reduces to 2/7. So that's how we take half of a fraction. Either multiply a 2 in the bottom and you're good, or it'll give you something that reduces further, and you do that. So the square we're completing, x minus what? Half of 4/7 is 2/7. Half of 4 something is 2 something. Half of 4/7 is 2/7. And then always plus, we're squaring this. 2 squared is 4. 7 squared is 49. So plus 4/49 completes that square. One more, and then we'll connect this to actually solving something. W squared plus 7/3 W. It's not an even, so we can't do that cool half of 7 something is half of 7 something. But half is still multiplying by 2 on the bottom, so half of 7/3 would be 7/6. 7/3 times 1/2, 7/6. And then we square it. 7/6 squared would be 49/36. So adding 49/36 completes the square there. Okay. Why is this useful? Well, because we're about to use the square root property to solve x squared minus 6x plus 13. Equals 0. Okay. So we wouldn't be able to solve this by factoring because this does not factor. We can't just get the x squared by itself because that still leaves x's on the other side. And this is not a perfect square trinomial, so we can't just make it something squared on its own. So here's how we use completing the square. We're going to go ahead and start by subtracting the 13 from both sides. And I'm going to leave a space where that's blank, plus 13 minus 13. Those go away. And on the other side, we have this equal negative 13. By getting rid of the constant, however, we have to move it to the other side using algebra, we have now set up that completing the square problem that we've done a few times now. So we got to find the number that we put in here. Here's the catch. Just like subtracting 13 from one side means we have to subtract 13 from the other, here, when we create this number that completes the square and we magically put it on the left, we also need to add it to the right because there isn't magic in algebra. Whatever we do on one side, we have to do to the other. It's the rules. So let's complete the square. It's going to be an x minus. Half of 6 is 3. 3 squared is 9. So plus 9. Not minus 9, because negative times negative is positive. The number we put is always going to be plus. I just put this plus 9. I created it out of nowhere. I'm going to add 9 to the other side as well. Now it's balanced. I'm allowed to add 9 to the left as long as I add 9 to the right. Negative 13 plus 9. It moves us towards 0, but not enough for it to be positive, so it'll still be negative. Negative 13 plus 9 would leave us at negative 4. Now we can use the square root property. We completed the square. Now we can take the square root of both sides. The square root of x minus 3 squared just leaves us with x minus 3. On the other side, we have plus or minus the square root of negative 4. Let me move that up to the top so we can continue working. Whenever we have the square root of a negative number, we want to make that I times the square root of the positive. The square root of 4 is 2, so this is x minus 3 equals plus or minus 2i. Add 3 to both sides. X equals 3 plus or minus 2i. 3 plus 2i, 3 minus 2i. And now you can see another reason why adding 3 to both sides is going to put the plus 3 in front of the plus or minus. It keeps us in a plus bi form when we get complex answers. So 3 plus or minus 2i. If we were specifically told the answer should be real numbers only, there would be no solution. But if it doesn't say just real numbers, if we can use complex numbers, which, unless specifically stated, it has to be real, we can now take square roots of negative numbers using I. Let me do another. Two m squared plus 10m equals 3. Now, if I leave some space, we can see we already just have what we need to complete the square on the left, but I want to caution you. Caution, caution, caution. So sorry. Caution. We have not done a completing the square that had a number in front of the m squared or the x squared or the whatever squared for a reason. And it's because you can't do the completing the square trick when you have something there. So whatever's in front, we're going to divide everything by that number. So that gets divided by 2, that gets divided by 2, that gets divided by 2. I would have just said, hey, let's divide both sides by 2, but I don't want you to get it twisted. I don't want you to think that nothing happens to the 10. I want to express that dividing a whole side by 2 means dividing each term by 2. And what's this give us? This gives us m squared plus 5m equals 3 over 2 is 3/2. Completing the square. Well, what's the square we're going to complete? It's going to be an m. It's going to be a plus. Half of 5 is 5 halves. 5 halves squared plus 25 fourths. If I'm 25 fourths adding on one side, I will 25 fourths add on the other, because them's the rules. And how do I add two fractions? Well, I get a common denominator. 3 halves is 6 fourths. You're starting to see it now. You're starting to see why we did the things that we did at the beginning. Why we have to know how to add fractions by hand. Because they're mini steps in larger problems. This is not foundations of algebra. This is intermediate algebra. This isn't even college algebra. So you're expected to know these things. How to add fractions. Completing the square, solving, doing that, that's the new thing. And while the places you might screw those up are in the little details of the adding and subtracting, that might be what makes it difficult for you. That's not this class's material. So I'm going to show the steps as much as I can. But 3 halves plus 25 fourths, I shouldn't be needing to explain it. I'm refreshing your memory. Hopefully I'm not teaching you straight out here. Let me move this bottom line to the top so that I have some space to work. M plus 5 halves squared equals 6 fourths plus 25 fourths. Okay. 6 fourths plus 25 fourths is 31 fourths. So we have this square by itself, all on its lonesome, equal to something else. What do? Square root both sides. Square and the square root cancel each other out, just leaving us with m plus 5 halves. Over here, we get plus or minus the square root of 31 over 4. Watch what happens here. This is beautiful. Rationalizing, right? 31 over 4, we can't simplify it, but because it's the square root of a fraction, that's like having square root over square root. And we don't know what the square root of 31 is. We can't simplify that at all, but we do know what the square root of 4 is. M plus 5 halves equals plus or minus square root of 31 on the top, 2 on the bottom. Doing this twice in one problem, writing it up top. M plus 5 halves equals plus or minus radical 31 over 2. I'm going to subtract the 5 halves to get the m by itself. So I have minus 5 halves plus or minus radical 31 over 2.